In this presentation, we're going to talk about multiplexing and demultiplexing. This fits into what we've been studying so far, in that multiplexing and demultiplexing are just special cases of truth tables. So we're going to study them as such, but we're also going to look at their role within computing. Now, the computer gets its name, and the processor gets its name by sort of taking some data, acting on it in some way, and getting some new data. We're processing, we are computing, but there's an awful lot of just moving the data around in order for that to happen. So we need to retrieve an instruction so we know what it is we want the computer to do. We have to get the data that is going to be acted on by that instruction. Then we have to take the answer and put it in some appropriate location. Lots of moving around. The design of a computer often has shared information channels, or what's known as bus or buses. And so instead of having direct connections from every possible point to every other point, we have this shared channel that gets us most of the way there. So the path from point A to point B and the path from point C to point D will share a lot of this bus, this shared information channel. And then it is the job of the multiplexer and the demultiplexer to sort of do the sharing. So we need to make a decision at a given instant which of all the possible sources of data is going to get through. That's the job of the multiplexer. And which of all the possible destination is going to get the answer. That's the job of the demultiplexer. In multiplexing, there is some carrier, some channel, something that will support a signal of information being sent. There are two sort of standard ways to do multiplexing: frequency-division multiplexing and time-division multiplexing. In frequency-division multiplexing, the medium can support multiple signals simultaneously, and then the information must be prepared by the center so as not to interfere with other signals, and then it is picked up by the receiver by sort of tuning in. So think of radio stations. So the information is sent out by many radio stations, and then the receivers can listen to those radio stations by tuning in. They are picking out the frequencies at which the signals are sent. And so that's why it's called frequency division. The sort of organization of the signals so they don't interfere is done by giving them different frequencies. In time division multiplexing, the medium is a much simpler medium, more like a wire or some wires. And they do not support multiple signals at the same time. Rather, they get multiple signals sort of by sharing in time. So at one instance, a given signal is being sent, and then later on a different signal. And so they are taking turns using the same simpler channel. Time division multiplexing gets further broken down into sort of standard time division multiplexing and statistical time division multiplexing. In standard time division multiplexing, all the possible sources of information are sort of going to take equal turns in putting their information onto the channel. But in statistical time division multiplexing, there will be some analysis to see sort of which source has more data to be sent, and then that might get a higher priority, more time on the wire. But we're not going to worry about the timing or the sort of sharing or weighting of the timing whatsoever. We're just going to be interested in this very low level, how do we select? So we're going to have bits of information, but we will have possible sources of a bit of information, and then we want to pick one of those sources to get through and be put on the channel. It's important that you understand that we are not sort of combining signals in any way. We're not putting them through an AND gate or an OR gate. We will have some mechanism to pick one of the sources, say source number 3, and then that bit, whatever it was, high or low, is what gets through the channel. So we're not combining it in any way with other channels. It is selected and then it gets through. The others are blocked. End of story. In this presentation, we're going to be more interested in the time division multiplexing. So we will have a number of sources, in this picture 1, 2, 3, and then we will have a device known as a multiplexer, and the job of the multiplexer is to pick out one of those signals to be placed on the shared channel at a given instant, and then at another time choose another one. So we're not going to be worrying about the timing, we're just going to be worrying about the actual selecting. So what's in the multiplexer then allows at a given instance for us to choose source number 2 to get through and be put on the shared channel. So a multiplexer is a device that has several data inputs, and it's going to have one output. And that output then may be connected to a shared communication channel. In addition to the data inputs, there are going to be what we call select inputs. So the data input is the information that wants to get through, but there are several of them. And then it's the select input that is going to pick which one of the data inputs gets through. And then next we'll look at the question of how many select inputs, how many select pins will we need, and that will depend on the number of data inputs that we have. So we're going to think of each of the data sources as being numbered, or as we say, having an address. And then when we want to pick one of those sources, we will use the other set of inputs, the select inputs, to identify the address that we want. So if we wanted data number 2, then we would enter a 2 into the select inputs, which I will also now start calling address inputs, sort of interchangeably. You use an address to select something, so I'll call them select inputs or address inputs. So now we have one of our favorite questions from binary numbers. If we have so many source inputs, then how many select or address inputs do we need? Or let's turn the question around. It's a little easier to ask the other way. So if we have 1 bit, that 1 bit can be in 2 states, high and low, and thus it can distinguish from 2 things or 2 sources. If we have a 2-bit address or 2-bit select, that can be in 4 states, 0, 0, 0, 1, 1, 0, 1, 1, and thus can be used to address 4 different sources. 3 bits can be in 8 states, which are shown on the slide, and in general, n bits can be in 2 to the n states. So now let us talk about some of the nomenclature of multiplexers. How do we talk about them? What vocabulary words do we use in the context of multiplexing? So another term for a multiplexer, just a shortened version of the word, is MUX. And therefore a MUX, being a multiplexer, will have several data inputs and 1 data output. And so if it has, in general, n inputs and 1 output, we will call it an n-to-1 MUX. So we will talk about 2-to-1 MUXes, 4-to-1 MUXes, 8-to-1 MUXes. Typically, the n is some power of 2 because, again, they need to be addressed. And so if we have some number of address or select inputs, then the number of things we can distinguish is usually a power of 2. So when we're talking about an n-to-1 MUX, that n is usually some power of 2. And then the number of address inputs is just the opposite of what we were doing before. So it's log base 2 of n. In case you don't quite know what I mean by log base 2 of n, I'm giving you a list here of n and log 2 base n for different powers of 2. Remember, our n's are going to be powers of 2. So if n is 2, then log base 2 of n is 1. Again, this n is the number of data sources, and the log 2 of n is going to be the number of selects. So if I have 2 data inputs, I need 1 select. If I have 4 data inputs, I need 2 selects. 8 data inputs requires 3 selects, and so on. So in the multiplexer, in the MUX, we have data inputs and select inputs. But we're going to just move into considering it to be a truth table, and so they're just inputs. And the output depends only on the inputs for a multiplexer. So we say that it is combinatorial logic. Combinatorial logic means just what we just said, that the inputs lead to the outputs, and you don't need to sort of remember some previous state that has nothing to do with it. It's just whatever the inputs are tell you the outputs. So such logic is called combinatorial. If you need to remember some previous state, then you are said to have sequential logic. But a multiplexer is combinatorial logic. Therefore, it's just some kind of a truth table. So now let's write out the logic of a multiplexer as a truth table. So here we see the full-blown truth table for a 2-to-1 MUX. A 2-to-1 MUX has two data inputs that we're labeling D0 and D1. It has one output, shown over there is the output of the truth table. And then to pick between the two data sources, we need one address or one select, and that's labeled A. So with three inputs, one select and two data, that's three inputs altogether, and that leads to 8 possibilities, 8 combinations of zeros and ones, so they're all shown here. When the select A is equal to 0, then the output should be equal to the input D0. And when the select is 1, then the output should be equal to the D1 input. And that's how we've set up this truth table. That's what a multiplexer does, and this is then the truth table for it. And so once we have the truth table, we can take our usual sum of products approach, so we can focus on the ones in the output and write the AND expressions for each one. And you'll see that here, A prime D0 D1 prime plus A prime D0 D1 plus A D0 prime D1 plus A D0 D1. And the first two terms have the A prime D0 in common, and factor out a D1 prime plus D1, which we know that is equal to 1. And similarly, the third and fourth terms have A and D1 in common, and a D0 prime plus D0 factors out, and that is also 1. And so when we work it all down, we have A prime D0 plus A D1. And we can also, if we want to, take a Karnaugh map approach. So here's the Karnaugh version with the D0 and D1 inputs going down in the rows and the select A input going across the top. And we find that we have two groups, one with an expression of A prime D0 and the other one with an expression A D1. And so here's the 2-to-1 MUX in gates. So there were three inputs. The A is the select input, and then two data inputs labeled 0 and 1. And so we have two ANDs, the A prime D0, and the other one, the A D1, and then they are ORed for a simplified sum of products approach. So here we have a version of the truth table for a 4-to-1 MUX. So a 4-to-1 MUX has 4 data sources, 1 output, and then to pick among the 4 data sources, we need 2 addresses or 2 selects. So altogether there are 6 inputs, 4 data and 2 select. And if you're going to write out the truth table in terms of all possible combinations of 0 and 1, there would be 6 inputs. Therefore, there would be 2 to the 6th combinations, or 64 rows in the truth table. So this is sort of a condensed version of the truth table. Let's look at it. So the select inputs A and B are all the combinations are written out, 0, 0, 0, 1, 1, 0, 1, 1. The data D0, when we write D0, that just means it could be 0 or 1. Same for D1, same for D2, same for D3. And then in that first row, when A is 0 and B is 0, then the output is whatever the input D0 is. When the select, in the second row, when the select input is A is 0 and B is 1, then the output is whatever the D1 input is. When the select input is 1, 0, we are selecting D2, and so the output D2 is equal to the input D2, whatever it is, 0 or 1. And finally, when A is 1 and B is 1, we are picking D3, and so the output is whatever D3 was. So this is just a succinct way of expressing the truth table without writing out 64 possibilities. When we simplify the 4-to-1 MUX, what we get when we're done is all the combinations of AB, A prime, B prime, A prime, B, AB prime, AB, and then each one is associated with one of the data inputs. So A prime, B prime, D0 plus A prime, B, D1 plus AB prime, D2 plus AB, D3. So the data inputs are never primed, and we get all possible combinations of AB, and each combination of AB is associated with one of the data inputs. So to recap, we had 4 data sources. Each data source, each data input was assigned a specific state of the select or address input. So there were 2 address or select inputs, so the states were low, 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 high, high, low, and high, high. Those are the possible states of the address inputs. Each of these states can be thought of as a binary number, 0, 1, 2, or 3. And so those 2 selects lead to 4 addresses. And so this is how the data inputs are addressed. So they are assigned a number, and then they can be picked out based on that number. And this is sort of pervasive in computing. Anytime you want to distinguish 2 things, you can sort of assign them an address and then pick one from the other using a technique like this.